Hello, this is Brad Strivig. Today we're going to continue our discussions about acid bases, and in particular, calculate the pH and pOH associated with acids and bases dissolved in aqueous solutions. If we have acids dissolved in water, the acidity or strength of the acid is determined by the equilibrium constant. The larger the value of the equilibrium constant, that means the greater the production of the proton H plus in solution. So for very, very large equilibrium constants, we can assume that there's so little of the combined acid, the HA in solution, that essentially all the acid forms H plus and A minus in solution. And this occurs for an acid that completely dissociates. That means, again, there's so much H plus in solution and A minus in solution from the original acid, HA, that essentially there's no HA in the form HA dissolved in solution. This is known as a strong acid. A strong base, then, is one in which we have the same process, where something combined with the hydroxide ion, OH-, also completely dissociates or completely dissolves into the ions into solution. A common one you might be familiar with is sodium hydroxide. So sodium hydroxide has a very large value for Kb. When we put sodium hydroxide into solution, it dissociates completely to form dissolved sodium ion, Na+, and the hydroxide ion, OH- into solution. And this would be an example of a strong base. The pH of a solution, then, is simply a measure of the hydrogen ion in solution, and P is a mathematical operation symbol for the negative logarithm. So we can replace the symbol, mathematical symbol, negative logarithm, with a lowercase p. And in this case, we place the activity brackets or concentration brackets for H plus with just the symbol of H. You might be familiar with what the pH of a neutral solution is. So what is the regular pH of tap water? Well, tap water is a little tricky, as we'll discuss. Depends on what the dissolved gases are. But in a pure water solution, if we were to only have H2O and nothing else dissolved in the solution, then there would be some dissolved ions of H plus and OH minus from the water. The value of those ions, H plus and OH minus, is very, very small, and as we multiply those together, they're equal to 10 to the minus 14. That gives us an equilibrium expression for the pH, and the H plus concentration is 10 to the minus 7th moles per liter of H plus in solution. Very, very, very little acidity, very, very, very little basicity, and in fact the two are equal in a neutral solution. So we find the pH then of this solution by just taking the negative logarithm of the H plus concentration. In neutral water, since the H plus concentration is 10 to the minus 7th moles per liter, the negative logarithm of that value is 7. Thus, the pH of neutral water, a pure water solution, is 7. We can define the pOH in a similar fashion, where the pOH is just the negative logarithm of the activity of the hydroxide ion in solution. As we've said, we can have a water acidity constant, which is the products H plus times OH minus over the concentration of water. Recall that the activity water was defined as 1, so we're left with a special activity constant for water that's labeled Kw. Most activity constants are K sub A, but water has this special activity constant because it's so ubiquitous. It's given its own special term, K sub W. And it's equal to the hydrogen ion concentration times the hydroxide concentration, and the constant at 25 degrees Celsius is 10 to the minus 14th. If we take the negative logarithm of each side of this equation, so the left-hand side would give us the negative log of Kw, that would be equal to taking the negative logarithm of the right-hand side, the negative log of H plus plus the negative log of OH minus equal to the negative log of 10 to the minus 14th. On the final line down below, the negative log of 10 to the minus 14th is equal to 14. The negative log of kW is, by definition, P times kW. Similarly, negative log of pH is pH plus pOH is equal to 14. So if we know the pH of the solution, we can very quickly get the pOH and thus the hydroxide ion concentration. Likewise, if we know the hydroxide ion concentration in water, we can very quickly find the pH of the water. So we'll do multiple analysis where we determine the pH of solutions because the pH is a master variable that controls the concentration of other parameters in solution as well. In order to do this, first we would define the system boundaries. So if we have a glass of pure H2O with nothing else dissolved in it, pure even than tap water, at 25 degrees Celsius and 1 bar, or standard temperature and pressure, we define the system boundaries as a container. All the species that would be in the pure H2O would be the water molecule itself, H2O, but that's in equilibrium with some H plus in solution and some OH minus in solution. Then we can write the chemical equations for the system. We write the relevant equilibrium equations, the electroneutrality equation, and any equations that can help balance the mass of all materials in the solution. In your textbook, these are equations 240, 245, 246, and 249. In this case, this is a pretty simple system, the simplest aqueous system in fact, so we don't need to make any simplifying assumptions. We have then for the acidity constant, Kw is equal to H plus times OH minus. By definition, from electroneutrality equation, if that's written down, all the positive ions must equal all the negative ions. So the H plus concentration must equal the OH concentration. Then we can substitute from the electroneutrality equation into the acid equilibrium equation. So the Kw for a neutral solution is going to be equal to H plus times H plus, or the activity of the hydrogen ion squared. And that value is a constant at 25 degrees, which is equal to 10 to the minus 14th. When we solve then for the activity of H plus, just as a variable, taking the square root of 10 to the minus 7, we see that that is indeed taking the square root of 10 to the minus 14th to solve for H plus squared. Solving for H plus, taking the square root of 10 to the minus 14, we get H plus is equal to 10 to the minus 7th. From electroneutrality, the H plus concentration is equal to the OH minus concentration, and we get a value of 10 to the minus 7th moles per liter. The pH then is the negative logarithm of the H plus concentration, which is the 10 to the minus 7th, plus the pH is 7. Likewise, the pOH can be found from the hydroxide ion concentration from the electroneutrality equation, which is also equal to 7, or from our logarithmic relationship between pH and pOH, since we know that the pOH is 14 minus the pH, again giving us 7. This may seem very simple, but these are very, very powerful tools that we can use to solve any equilibrium expression. So for things like a chemical spill, an acid or base spill in a moving body of water or a lake or pond, we can actually determine the pH following the same process and same simple steps described herein. And we'll do that in the next couple sections.